So in this module, we are going to discuss the matrix method of structural analysis. There are two methods. So we already had some introduction yesterday. So one is called flexibility method, and next one is the stiffness method. Okay. So flexibility method is basically a force method of analysis. Your primary unknowns will be forces, and the stiffness method will be it is a displacement method of analysis. So we have seen what is stiffness and what is flexibility method in very short. So today we will discuss how to so today we'll see in detail what is the flexibility method, how to form the flexibility matrix for a given structure, okay, or how to analyze the your structures by using flexibility methods. So that is what we are going to discuss today. So I'll try to complete it by today. The flexibility method for beams. So we have to discuss flexibility method application to beams, and next how to solve the pin jointed frame trusses. Okay, same thing for the stiffness method also. The stiffness method application to the beams and application to the trusses. Okay, that is the four parts we can say in the syllabus. The first stiffness flexibility method, beams and truss, and stiffness method, beams and truss. Okay, so today I will try to complete flexibility method for beams. Okay, so the procedure explained in these slides. Okay, step by step we can go through that. So I will just explain and there whatever I have written in the slides. So I think it is better. I will write and I will explain. Okay, that will be better. Okay, so after discussing, you can go through that slides. You will be able to understand it properly. Okay. So, okay. So let us take a continuous beam and then see how to form the flexibility matrix for a given structure. Okay. So let us take a continuous beam. The same thing. Whatever I have explained in the slide, we will take the same structure. This is a continuous beam, three span continuous beam, and we have some loading also. Okay. So let us take that. So let us take a continuous beam. So one end is fixed, and let us have here we have support, and here also, and we have some loading UDL in the second span, and here we have some point load maybe at the center. Okay, the first step is find out static indeterminacy. Okay, so we can say that for a vertical load, early vertical reaction will be there and moment, and here we have vertical reactions, and here I have vertical reaction, and here I have vertical reaction. So total we have five. How many unknowns? So 1, 2, 3, 4, 5 unknowns. So 5 minus equations are 2. Okay, 5 minus 2, 3. Because we are taking only two equations because we are not considering the horizontal reaction. So sigma fx equals 0, that equation also we are not considering. So static indeterminacy equal to 3. So okay, that means we have three the extra unknowns we have in this case. So three redundant forces we have in this structure. So because we are finding static indeterminacy first, because it is a flexibility method, it is a force method of analysis. That is the first step. Okay, simple. Find out static indeterminacy, and now your job is the next step. You have to identify, or you have to choose out of these five unknowns. You have to take any three. You have to remove any three unknown from your structure so that you can get a basic determinant structure. That is my second job. Okay, the second step is I choose any three forces as your the redundant forces in your problem. So let me choose 1, 2, 3. These three vertical reactions are the let us say these are the three redundant forces in my case. Okay, let me write this is maybe A. I think this is not required. A, B, C, D. Maybe you can write like this. So in this case, we can say this is RD. This is the reaction at the support. Maybe RD. Okay, I will write R1, and it is R2, and it is R3. Okay, that is a that is what I am doing the second. Okay, choose any three as your extra forces. Choose R1, R2. You can choose any one, any three. You can choose moment. You can choose any three. No problem. Only thing is after that your structure should be stable. So maybe this may be the best option, I would say, because even though if you remove these three, still it is a stable structure. It is a simple cantilever beam. It is a stable structure. So R1, R2, R3 are okay. So that is the second. So now we remove the now you can remove these forces R1, R2, R3. So once you remove it, what you will get? You will get a basic. You will get a basic determinate structure. So BDS. You will get a basic determinant structure, and let us say I am applying the same load as in the case of the given structure. So you just remove the three unknowns, three reactions, and now you will get a basic determinate structure, and you apply the same load, whatever is the load given, and you apply that, and you find out your deflection in this beam. Okay, so this beam is going to deflect like this. So you can find what is the deflection at this point 1. So we will also give a coordinate we have discussed yesterday. So let me call this is coordinate 1, it is coordinate 2, just to identify the location. Okay, it is coordinate 3. 1, 2, 3. These are the coordinate. Okay, this is a point location 1. It is joint 2. It is 3. Okay, so at this location, at this coordinate 1, due to the external load in the basic determinant structure, we can find out the deflection. Let me call that is delta 1. And the next is this point, you can find the deflection delta 2, and next you can find the deflection in the basic determinant structure due to given load at this location, that is delta 3. So why I am calling delta 1 this, delta 2 this, delta 3 this, because I am calling this is the coordinate 1, it is a point 2, it is a point 3. So if you define 1, 2, 3, then it will be delta 1, delta 2, delta 3. Okay, you can do whichever way you like. Okay, that will not make any difference. So that is the next step, maybe you can say. Next, you in the basic determinant structure, once you remove these three extra unknowns, you will get a basic determinant structure. The basic determinant means it should be stable also. Okay, so cantilever beam is anyway it is a stable structure, and in the basic determinant structure you can find the deflections at this point wherever these are the point I have removed my reactions supports. Okay, so that's why I am finding the deflection at those point delta 1, delta 2, delta 3. Okay, so that is my next step. Okay, and the next, in the fourth step, you will take same, you take the basic determinant structure. Okay, you take the basic determinant structure, and without taking any external load, you remove all the external load and take your basic determinant structure, that is your cantilever beam, and don't take any external load. Okay, and then you apply a unit load in the first coordinate, then you apply a unit load in the first coordinate, because I have removed the reaction R1, that is why I am applying a unit force. I can also write it is 1 kilonewton or 1 newton, whatever it is. It is a unit force I am applying. Okay, suppose you have removed in any problem, if you have removed this moment as a redundant reaction, then you have to apply unit moment in that case. Okay, that depends what is your type of force which you have removed. You have removed unit, you have removed the reaction some kilonewton or some newton, it is a force, that is why I am applying a unit force at the coordinate 1. Apply a unit force in the same direction as my assumed direction. Okay, so this is my beam, I have assumed this reaction R1, R2, R3 in the upward direction. Okay, that is why I am applying the unit force at location 1 at this coordinate 1 in the upward direction. Okay, suppose if you have assumed in the downward direction, then you can apply the unit force in the downward direction. Okay, and of course it is very clear that this reaction will be downward, it should be upward direction, it cannot be in the downward direction. Okay, so that is why better assume in the correct way. Okay, even though if you assume in the downward direction, you will get correct answer with a negative sign, then you can change it later on. Okay, but it is very clear that this reaction must be in the upward direction, so I will be assuming R1, R2, R3, these are my unknowns, it will be in the upward direction, the direction is already known to us. Okay, only magnitude we don't know. Okay, so apply unit force at the coordinate 1 in the upward direction. So once you apply the unit force, what will happen? Your beam will deflect. Your beam will have a deflection in the upward direction. It will bend like this. So it will deflect something like this. Okay. So now you can find in this basic determinant structures, it is subjected to only unit load at the location 1 in the assumed direction. So now we can find what is the deflection at the coordinate 1, and we are applying the load at the coordinate 1. So I will be calling this is F11. So in this case, there will be some deflection in the coordinate 2, and there will be some deflection in the coordinate 3 also. And this one I will be, this is my, I will give the nomenclature something like this. This is F21. That is a deflection at 2, unit load at 1. This is F31. Deflection at coordinate 3 and unit force at coordinate 1. So that is why I have to define this coordinate 1, 2, 3. Then only I can give this naming easily. Okay. So generally you can say that. Okay. Similarly, similarly you can take again you can take your basic determinant structure. Okay, and you apply unit force at the coordinate 2. Apply the unit force at the coordinate 2. Okay, and because of this load, again it will have deflection. It will deflect like this. It will have a deflection in the upward direction, and again you can find your deflection at coordinate 1, and deflection at the coordinate coordinate 2 will be here, and coordinate 3. So what we'll call this, it is a deflection at coordinate 1, and your unit load is at coordinate 2. Okay, this is your 1 kilonewton, and this is your deflection at coordinate 2, and due to unit load at coordinate 2. Okay, this is my deflection at coordinate 3 due to unit load at coordinate 2. Okay, similarly you can do it for the third coordinate also. You take your basic determinant structure, and now you apply your unit force at the coordinate 1 kilonewton. So due to this load, it is going to deflect. We have a deflection. So now we can find what is the deflection at coordinate 1, deflection at coordinate 2, and deflection at the coordinate 3. So this will be, what you will call this one, this will be reflection at coordinate 1 due to load at coordinate 3. So F13, it is called F23, and this is your F33. Okay, so generally I can write like this. Generally I can say this Fij. Okay, that means displacement at coordinate I due to unit load at coordinate j. Okay, it is nothing but your displacement at I due to unit force at j. Okay, so displacement can be anything. Displacement can be, it can be vertical deflection. This we already discussed. It can be deflection as well as theta. Okay, unit force can be a unit, it can be a vertical load. Also, it can be a moment. Okay, because here we our the redundant forces are reaction. So I am applying unit force. I am finding out finding out the corresponding deflection only. Okay, if it is a moment, we can find corresponding rotation. Okay, instead of this deflection. Okay, that depends what is your reaction. Okay, whether it is a moment or a force, it depends. Okay, so that is your fourth step. Okay, that is my fourth step. Okay, so now what will be the now we can write like this. So now we can find deflection at various coordinates, deflection at various coordinate location due to the redundant forces R1, R2, R3. So these are the reactions actually I have R1, R2, R3. I don't know the magnitude. So let us take the magnitude as R1, R2 and R3. So now I can easily find out that what is the deflection at various coordinate. Okay, deflection at various coordinate, that is 1, 2, 3 in this case, due to various coordinate location due to forces, due to your redundant forces. So can you tell me, if let us say R1, R2, R3, that is the actual forces we have. So what is the deflection at location 1, at the coordinate 1? This is the coordinate 1, 1. So this is the coordinate 1. What is the total deflection due to R1, R2, R3? So now we will take our basic determinant structure, okay, and let us say we have that reaction, it is acting R1, R2, R3. So we are applying this reaction as an external force, okay. So it is going to deflect. So next you take a basic determinant structure, cantilever beam, and apply your actual forces R1, R2, R3. These reaction you apply as an external force. It is not support, it is an external force you apply. So it will have a deflection delta 1. Let us say it is having some deflection here delta 2. It is having some deflection at here delta 3. So now can you tell me this delta 1, delta 3 in terms of your R1, R2, R3 and this coefficient F1, F11, F21. So what is the value of delta 1? What will be delta 1 equal to how much? Can you tell me? You can easily get that.
Delta 1
WLQ by
LQ
3A.
Delta 1 is equal to, I am asking
R1
this one,
LQ
okay.
by 3I
R1
LQ
R1
R1LQ
LQ
by
by
3.
so the R2 also, we R2, R3 also there. There will be some contribution of R2 and R3 also at this point, right? So we have to take that one also. Okay, anyway, I will tell you that. Okay, so let us take this one. If this is one a unit force is acting, suppose the R1 is acting, then what is the value of this deflection? Can you tell me? And instead of this one, R1 is acting, then
R1
what will be
LQ
the
by 3EI
no, I forgot about L cube. You tell me in terms of this coefficient
uh,
F11. What will be the value? Here 1 kilonewton, I have deflection at the coordinate 1 is F11. And instead of 1, I have R1. Then what will be the value of this deflection? F11. What will be the value of this deflection at this point? Instead of 1, I have this one. Okay, 1 kilonewton, I have deflection is let us say 5 millimeter. If I have 2 kilonewton, what will be the deflection? What will be the deflection? I have load is 1 kilonewton, deflection is let us say 5 millimeter, and instead of 1 kilonewton, if I apply 2 kilonewton, if I apply the double the load, what will be this deflection? The deflection also will become double, or it will not change. What is the value of deflection? If it is 1 kilonewton and I have F11 and now I have R1 kilonewton, then what is the value of this deflection? What is the relation between deflection and your load? What is the relation? How it is there any relation between your load and deflection in your structure? Is there any relation between your load and deflection? The load is proportional to deflection, that is simple. Because we are analyzing all the systems are linearly elastic range. And if you see a cantilever B, your deflection WLQ by 3I, something like that. And deflection is equal to WLQ by 3I. So that means deflection is proportional to W. So deflection, if you double the load, your deflection also will get double, because we are in the linear elastic range only. That is what your equation, all the equations we can use only in the linear elastic range. Okay, so that is what we are applying all superposition principles and all every time. Principle of superposition is applicable only if you are in the linear elastic range. So that if I double the load, I can your difflection also will get doubled. I can take individual effect and I can just take sum of those. Okay, so now I think you should tell 1 kilonewton I have deflection is F11 and instead of R1 instead of 1 I have a load is R1 kilonewton I am applying here. Then what is the value of deflection at this point and this point? What will be the value of deflection? This deflection will become how much? This deflection will become how much? F11 and what is the in terms of F11 you can tell me.
F11 into R1.
Yeah, F11 into R1. What is the value of this deflection? What will happen to this point? That will also F21 into R1. Okay, and this point, so deflection will be F31 into R1. Simple relation. So we have unit load. So that is why we are taking the unit load. Okay, we have the unit load. I can compute the deflection at this point. So now, if instead of unit load, if you are applying a 100 kilonewton, you just multiply these values with 100. Okay, that is what I am doing. So if we have R1, deflection at this point will be F11 R1, this will be F21 R1, this will be F31 R1. Similarly, next you can take this section here 1 and actual reaction may be R2 and instead of 1 if you apply R2, so what will be this value? It will become F12 times R2, right? This will become F22 times R2 and this will become F32 R2. Okay, and the next this one I will apply R3, then this deflection will become F13 R3 and this will become F23 R3 and this deflection will be F33 times R3. Okay, so now you tell me what is the total deflection at location at the coordinate 1 delta 1. What is the total deflection due to R1 R2 R3? What is the value of this small delta 1 is equal to how much? What is the value of delta 1 small delta 1?
F11 R1 plus F12 R2 plus F13 R3.
Yeah, so it will be F11 R1 plus F12 R2 plus F13 R3. That is the value of your total delta 1 small delta 1. Okay, and similarly small delta 2 will be equal to F21 R1 plus F22 R2 plus F23 R3. Okay, and next you can find this delta 3 small delta 3, that is F31 R1 plus F32 R2 plus F33 R3. Okay, so that is what I was asking. So we can write delta 1 that is equal to, so this delta 1 is basic determinant structure. We have removed all the external load and we are applying the redundant forces R1 R2 R3 as an external load. Okay, that reaction we are applying as an external load. So due to that, what is the value of deflection at the our coordinate location delta 1 delta delta 2. So delta 1 that will be equal to, so that is F11 R1 plus F12 R2 plus F13 R3. Okay, and similarly delta 2 it is equal to F21 R1 plus F22 R2 plus F23 R3. Okay, I think it's correct, and delta 3 is equal to F31 R1 plus F32 R2 plus F33 R3. Okay, so you have to just take the sum of this F11 R1, that is a deflection at the coordinate 1 due to R1. This is a deflection at the coordinate 1 due to R2. This is a deflection at the coordinate 1 due to R3. Similarly for other coordinate as well. Okay, this is the final. This is the deflection in the basic determinant structure due to your unknown, your extra reactions R1, R2, R3. Okay, so this one you can also write in form of matrix. So you can also write in form of matrix. So it will become delta 1, delta 2, delta 3. So this is a vector delta 1, delta 3, that is equal to, we can write in form of matrix. So some matrix here into, so I can write like this R1, R2, R3. Okay, so this what will be these elements? Elements will be F11, F12, F13. Okay, and this will be F21, F22, F23, F31, F32, F33. Okay, so in matrix form, these three equations I can write in the matrix form. Okay, okay, that is your maybe step number 4. Okay, step number 4, we apply the unit force. Then we are also we got the deflection in the form of matrix form, in matrix form. Okay, due to this R1, R2, R3. Okay, so now you come back to our the given structure. It is a given structure. Okay, your given structure is this one, a continuous beam. Okay, so first we have removed these support reactions, and I have delta 1, delta 2, delta 3. This is the deflection at these coordinate due to external load in the determinant structure. So now tell me, this is my real structure, and then what is the relation between delta 1, delta 2, delta 3, capital delta 1, delta 3, and this one, small delta 1, delta 2, and delta 3. What should be the relation? What should be the relation between this delta 1, delta 2, delta 3, and this delta 1, delta 2, delta 3? What should be the relation? So that means finally in the real structure, this point, what should be the value of deflection? It should be 0, because there is a support. We cannot have any deflection. This deflection should be 0. This one, all this the point 1, 2, 3. Actual structure we have a support, so your deflection must be 0 there. Okay, that means your downward deflection due to external load in the basic determinant structure, delta 1, delta 2, delta 3, and your upward deflection due to these redundant forces. Okay, these delta 1, delta 2, delta 3, these downward and upward deflection, it should be just equal. It should be equal. One is upward, one is downward. So if you take the sum, you will get your total deflection in the final structure, and that should be 0 finally. Anyway, that will be 0. Okay, the next you can find your total deflection. That is actually, that is your compatibility equation. Okay, that is what we will be calling the compatibility conditions. So now I can write the total deflection at coordinate location will be just summation of your deflection due to external load and due to the your redundant forces. Okay, so you can write your total deflection delta 1, total deflection, let me take it as d, that will be equal to, you can say, the your summation of summation of external load and so I can write, so you can write d1, which is equal to delta 1 plus small delta 1, and d2, which is equal to delta 2 plus small delta 2. So I'm just writing in form of equation delta 3 plus delta 3. So obviously we know that this d1, d2, d3, that will be 0 definitely, because this I have a support and we have some loading. Because what is the deflection at the coordinate 1? This is your d1 and d2, d3. Okay, so always this displacement may not be 0, that is why we are just writing in the form of equation. To get your total deflection, you have to take the summation of your deflection due to external load plus your redundant forces. Okay, so this is your equation that d1 is equal to delta 1 plus small delta 1, d2 is equal to delta 2 plus small delta 2, and d3 equal to delta 3 plus small delta 3. So now I can substitute this one, delta 1 delta 3, you can substitute this one. Okay, so that I'm not writing, already it is given. So this is what we got now. We are in steps number 6. So d1 equal delta 1 plus d and small delta 1, d2 d3 similarly. So d1 d2 d3 are deflection due to combined effect of your external loads and the redundance. Okay, so now we can substitute d1 is equal to delta 1 plus your small delta 1, and what is small delta 1? You can put this matrix delta 1 delta 3. So that you can write it like this, d1 d2 d3, which is equal to delta 1 delta 3 to the vector plus your small delta 1, that is this is your small delta, that matrix. Okay, so this 3 by 3 matrix into 3 by 1 matrix. So in short, I can write this is your F matrix, it is your R matrix, it is your delta matrix, it is your D matrix. So I can write D is equal to delta plus FR. Okay, this is my final equation, and here the D, it is the resultant displacement matrix. It is your final displacement values, and delta, this is a matrix, you can say it is a displacement matrix due to external load. How we are getting this delta 1 delta 2 delta 3? We are getting from here, we are getting, this is what we are doing, we are taking the all the external load in the basic determinant structure, that is delta 1 delta 2 and delta 3. That is why delta is known as displacement matrix due to external load. Okay, and this matrix, this 3 by 3 matrix, that we will be calling the flexibility matrix, and this matrix we will call the flexibility matrix. That will be 3 by 3 matrix, because in this structure, in our structure we have 1 2 3 coordinates, 1 2 3. Okay, or you can say your static indeterminacy is 3. That is why this flexibility matrix will be 3 by 3 matrix. Okay, this is known as the flexibility matrix, and this is your R matrix, the force matrix. Okay, so this is the final equation, D is equal to delta plus FR. Also you can write delta equal to, maybe you can write like that also, not delta, we have to find this one, no, redundant forces. So I can write R is equal to, from this equation, so R equal to, you can take D minus delta, that is FR, this divided by your F, right? So we can write F inverse into D minus delta. R is equal to F inverse F, you take the flexibility matrix coefficient, the inverse of that matrix, F inverse into D minus delta. That will give you the, by using this we can find out your the redundant force we can find out. Okay, and one more thing, we'll discuss that later also, like here these are the flexibility matrix, and each element of this matrix will be calling flexibility coefficient. Okay, flexibility coefficient. And what is the flexibility coefficient actually? That is what that Fij, that is the displacement at I due to unit force at J. Okay, and in this matrix the F23 means displacement at your coordinate 2 due to unit force at coordinate 3. Okay, F32 means displacement at 3 due to unit force at coordinate 2. Okay, that is the meaning. So by using, you can say you have must have studied already, by using, you must have studied that flexibility, that the Maxwell's reciprocal theorem. Okay, so by using that theorem we can write that Fij and Fji will be equal. Okay, Maxwell reciprocal theorem is saying like this. Okay, suppose if you have a suppose if you take this is coordinate y, it is point 2, and if you apply the load here, find out deflection here. Okay, and that will be equal to apply load here and find out deflection here, both will be equal. Okay, you are getting what I am saying. The reciprocal theorem, it is already there in SA1. So apply load 1 here and find out deflection here, that will be equal to apply load here and find out deflection here. Okay, that is what your reciprocal theorem is saying. So by using that condition, I can say that F23 means your deflection at 2 due to load at 3, and F32 means your deflection at 3 due to load at 2. F23 will be equal to F32. Similarly, all these F12 will be equal to F21, like that. All those terms will be just equal. We will see that in numerical examples also, and we will find that this will be always equal. Okay, so F12 will be equal to F21 and F13 will be equal to F31. All those terms will be just equal. So that is why you will find you can say that your flexibility matrix is a symmetric matrix, because this okay, so this F11 anyway, all the diagonal elements anyway, it is a common. F12 equal to F21, F13 equal to F31, F23 equal to F32. These are all just diagonal elements. So that means this matrix will be always, it is a symmetric matrix. Okay, whenever you derive a flexibility matrix, you can cross check that you should get a symmetric matrix always. Otherwise, you have done some mistake in the calculation part. Okay, that is a property of a flexibility matrix. Sometimes it is used to ask in exam directly. Flexibility matrix, it is a symmetric matrix. It is a symmetric matrix always. Okay, this is the procedure. This is how you have to develop a flexibility matrix for a Cuban structure. Okay, so I can make use of the flexibility matrix to get my the redundant forces. Okay, if I get all the unknown, if that is my objective, finally I have to solve the unknown reaction. So then I can solve everything. I can get bending moment, shear force. I can get all the result. Okay, that is a procedure in your flexibility matrix. So this we will see by taking some examples. We will see how to solve in a problem. Okay, so all these steps which whatever I have explained, it is given here. The first step, find out static indeterminacy 3 and assign coordinate 1 2 3. Okay, and step 3, these are you remove these redundants R1 R2 R3 from your structure to obtain a primary structure, which is a determinate structure, and the primary structure is statically determinate. It should be determinate structure, yes. Okay, and step 4, due to external load, find out your deflections at the coordinates 1 2 3, delta 1 delta 2 delta 3. That is a step number 4. After that, we can find unit loads are placed at this location 1 2 3, and due to each unit load, displacement at its own location and other coordinates are found out. Okay, apply unit load at coordinate 1, find out deflection here and also other coordinates. All other coordinates, you find out the deflection. That is what we have to do in this step. Okay, so I have explained this all those things. And what is the meaning of Fij? Displacement at I due to unit load placed at J. Okay, so you can just go through these slides. It is very easy to understand. So, and deflection at various coordinates location due to your redundant forces are F11 R1, F12 R2 plus F13 R3 equal delta 1, similar delta 2 and delta 3. Already explained. This we can write in the form matrix. Okay, and then we can substitute here to get your resultant deflection delta d1 d2 d3. Okay, and in this matrix we can say this is your finally your flexibility matrix. So maybe I will write one more sentence. The elements of flexibility matrix is known as flexibility coefficient. The elements of flexibility matrix is known as the flexibility coefficient. Sometimes in exam it will ask find out flexibility coefficient F12, F23, find out, like that. The short answer question can be asked. Okay, MCQ, I mean. The elements of flexibility matrix is known as flexibility coefficient. Okay, so to derive the flexibility matrix, very simple. You identify what is your coordinate 1 2 3 and apply unit load 1 and find out deflection all the point like this. Suppose your question can be like derive flexibility matrix. So okay, you have to derive the flexibility matrix for the given structure, that is your continuous field. Okay, what you have to do, you choose the three forces as your redundant forces. Okay, and then you apply unit load at location at coordinate 1. Okay, apply unit load at this point you have to remember, so that you can solve the problem very easily. First you apply your unit load at coordinate 1. Find out all the deflection f11, f22, f21, f31. Okay, what will be that these three elements? These three elements will form the first column, I will say first column of your flexibility matrix. Okay, you take your structure and apply unit load at coordinate 1. Find out all the three coordinate deflection, that is your first column of your flexibility matrix, f11, f21, f31, right? F11, f21, f31. Next you take you apply your unit load at coordinate 2, and you get all the displacement, all the three deflections, f12, f22, f32. What is that? That is simply your second column. And similarly you apply unit load in the third coordinate, you get deflections at all other coordinates, all the coordinate f13, f23, f3. That is your third column. Okay, this is what only you have to remember that will do to get your stiffness, your flexibility matrix. Okay, so this one we will do, and we will take 2-3 examples and we will see how to solve it. Okay, so I think it is clear. We will solve 1 or 2 examples, so it will be clear. It is not difficult. Okay, so I have given all the answers, everything here anyway. So first let us take an example. First take a cantilever beam. Okay, I have given solution, but I will solve it in the I will solve in the other side. Okay, so this is what given. A cantilever beam is given. Question can be asked like this only. A beam will be given and the coordinates are defined. Okay, so this is 1, your deflection component. This is my rotation component, 2. Okay, so develop the flexibility matrix. Okay, so here we have two displacement components are there. So our flexibility matrix will be, it will be a 2 by 2 matrix. It is going to be a 2 by 2 matrix. Okay, so what will be the elements of that matrix? That will be, you can write f11, f12, f21, f22. This is what our elements of the flexibility matrix. You can see the third one. You can see the f11, f12, f13. It is simply matrix. F21 means second column, second row, first column. F22 second column, second row. F23 second row, third column. F31 third row, first column. F32 third row, second column, like that. Okay, so we can directly say that your answer must be this matrix going to be 2 by 2 matrix, and f11, f12, f21, and f22. That is, these are the elements or flexibility coefficient. So our job is to find out f11, f12, f21, and f22. We have to find out this one. Okay, so now we can derive first column of your flexibility matrix. I can derive. What to do? You take your, this is my cantilever beam. So to get the first column, what I have to do? I have to apply unit force. This degree of freedom is given. Okay, this is translation 1. It is a rotation component 2. Okay, that is already given. So to get the first column, what I have to do? I have to apply a unit force in the same direction. Apply a unit force. Okay, and find out the displacement at 1 and force at 1, that is f11, and displacement at 2 due to force at 1, that is your f21. So your f11 is, what is your f11? I can say it is a deflection. It is your deflection at 1, deflection at 1 due to unit load at 1. So what is that value? So if you have a cantilever beam and apply a load of P, so what will be the deflection? This will be PL cube by 3EI, right? All the result you should know. So this f11 will be I have the load is 1, so it will be L cube by 3EI. That is your element F11. Okay, and what is element F21? What is the element F21? Not the equation. Can you tell me like this? What is F21 actually? What will be F21? That is a displacement at 2. Displacement at 2 means you have to see the direction. It is a rotation. Okay, the F21 means the rotation, because this displacement component is a rotational component. Okay, this is rotation at 2. Rotation at 2 due to, you have to understand very carefully, otherwise you will get just confused. Rotation at 2 due to unit load or unit force at 1. Okay, so again you can use the direct result. So if we have a cantilever beam, and this is the result we are referring, we have a cantilever beam and I have a unit, you have a force P, it is going to deflect like this. So we'll have a deflection of P L Q by 3 times EI, and we have the rotation at this free end, so that will be P L square by 2 EI. Okay, so now what is the value of F21? Here P is equal to 1, unit load we are applying, so 1 into L square by 2 EI. Okay, that is what I have written. This is your F11, L Q by 3 times EI, and F21, it is a rotation at 1, rotation, this rotation at 2, this coordinate, due to unit force at 1. So that is P L square by 2A, so L square by 2EA. This element is nothing but your F21. Okay, so next F2, that is my first column. Okay, that is my first column of your flexibility matrix. Okay, next we have to take, so I am just writing here only. Next we have to derive the second column. Okay, second column means two elements again, F12 and F22. To get the second column, what I have to do, you take your second column, take your structure and apply unit force corresponding to your second coordinate. The second coordinate is this one, rotation. So we have to apply unit moment. Apply unit moment. Okay, and then, so once you apply unit moment, you will have some, if you apply a unit moment like this, you will have some deflection and rotation. So maybe it may deflect, uh, so it may deflect like this. Okay, so if you apply unit moment at this, here we'll have some rotation theta, some rotation will have, and also will have some deflection. Okay, so we have two elements, F12 and F22. So what is your F12? F12, that is your displacement at 1 due to load at 2. Okay, displacement at 1, that means your deflection, displacement at 1 is corresponding to this one, so that is a deflection due to this unit moment. Okay, deflection due to unit moment, that is your F12, that means this one, that is, you can say, a deflection at 1 due to unit moment at 2. Okay, so you have to just follow whatever is the given degree of freedom. Here we have given like this 1 2, so that is why we are following the same. Okay, we have to follow the same. So this will be your F12. So what will be F22? That means your deflection or displacement at 2 due to force at 2. Okay, so what is your deflection, what is your displacement at 2 means you have to write your rotation. Okay, F22 means simple, you don't say deflection or rotation. F22 means displacement at 2 due to force at 2. Okay, what is the displacement in this case at 2? Displacement is a rotation, and what is the force at 2? Force also a unit moment. So I can write this is rotation at 2 due to unit moment at 2. So now we can directly use the result again. So we have a beam, we have a cantilever beam, okay, and we apply a moment like this M. So this will be your deflection in your beam. So this will be your deflection delta. This will be the theta. Okay, so what is the equation for delta? That is equal to m L square by 2 times Ci. So I will continue second hour also, okay, 12 to 1. So afternoon the Padma will take. Okay, the DCS will be afternoon. Okay, so afternoon I won't be taking any class. So 12 to 1 I will be continuing. So what is the equation for theta? ML by EI. Okay, so then you can tell B F1 deflection at 1 due to unit moment. We are applying a unit moment, so what will be this deflection? That will be ml square by 2a, that is 1 into L square by 2 times EI. Okay, and F22 rotation at this rotation due to this one F22 rotation at the free end due to the unit moment. Okay, so what is rotation? ml by EI. So you can take m is equal to 1, so L by EI. So F12 equal to L square by 2 EI and F22 is equal to L by EI. Okay, so that is what we have written here. This is your F, you can say this is my F12 and this is my F22. And you can see that F12 and F21 both are equal, L square by 2 EI. That is what the Maxwell's reciprocal theorem also saying. So F12 and F21 you will get same always. So now I got all the 4 elements, so you can say your flexibility matrix will be, so you can write the flexibility matrix if you want, you can just substitute and you will get the flexibility matrix. So this is how we have to derive the flexibility coefficient F11, F21, F12 and F22. So any doubt here you can just clarify now. We'll continue after that. If you have any doubt up to here, how to get the flexibility coefficient, is it clear or not? You can, if you have any doubt you can ask. So first you have to see the given degree of freedom displacement. One is a translation, so we have to apply unit force, and here we have to apply unit moment. Okay, and to get the first column of your flexibility matrix, you take your structure and apply a unit force corresponding to the first coordinate. The force, whether a unit force mean because it is given the translation, so we have to apply unit force 1 kilonewton. Okay, and in second column we have to apply unit force corresponding to the coordinate 2, because it is a rotational displacement, so we have to apply unit moment. Okay, remind thing is clear. So F12 means the displacement at 1 due to force at 2. Okay, F22 means displacement at 2 due to force at 2. Displacement can be rotation or translation, that depends. Okay, you have to see this one always. Okay, and force can be moment as well as unit reaction. Okay, so this is how we have derived F11, F21, F12 and F22. So these two will be always equal. So is it clear, this part? Okay, so it is not exactly a question, I have just put it in the slide. So development of flexibility matrix. This is how we have to develop your flexibility matrix. So okay, so now we can find delta 1. If we have a load of P, if we suppose at the free end, if we have a load is P and moment is M, so what is the deflection at the free end and what is the rotation at the free end? We can find out that also. Okay, so this is my structure. Let us say P is the force acting at the free end, and also I am applying the moment. Okay, also applying the moment also at the free end. Okay, so due to this load, there can be some there can be some deflection delta 1, and there can be some rotation also, that is for second delta 2. Okay, so you can also write directly that one, delta 1 is equal to due to unit load, what is the deflection? Due to unit load, what is the deflection? That is what here, LQ by 3EI, and when you have P, so that is just P into LQ by 3EI. So plus unit moment, this is the deflection L square by 2A, so due to moment M, so M L square by 2A, and this is equal to delta 2. It is actually a rotation at this point. So we can find delta 1, delta 2, we can write in this way also. Okay, and next we can write this one we have already seen. So delta 1 delta 2 that is equal to F11P plus F12M. Okay, and delta 2 is equal to F21P plus F22M. So I can put in form of matrix F delta 1 delta 2, F11 F12 and PM. So final equation will be like this: delta is equal to F into R, and where your F is the flexibility matrix. It is not exactly the question. If your question is a flexibility matrix, you can just do this much. You can just do this much, and you can write the matrix. That's it. Okay. So this is the rotation and deflection, and that I can write in form matrix finally. Delta is equal to F into R. Okay. So this is a simple example. Through that we have seen how to derive the flexibility matrix. We have to follow the same procedure. Only thing is here, because it is a cantilever beam and unit moment, unit force, I can easily write my equation for the deflection and slope. These results are well known to you. Otherwise, we have to find out this one. That will make it little bit difficult when you come to continuous beam example. Okay, but after that the procedure is very straightforward. Only thing is you have to get this value, unit moment, unit force, what is the deflection, what is the rotation at different points. You should know that. Okay, at least all the standard result, all the direct standard cases, you should remember the result for rotation and deflection, so that you can directly use that equation to derive the flexibility coefficient. Okay, later on, flexibility coefficient can be used to solve your R matrix. Okay, the random forces also can use that. Okay. So that will explain in the coming problems when we are solving the continuously. Okay. So this is where F, and maybe you can get some points here, some notes. So in the flexibility matrix, Fij denotes element in the ith row and the jth column. Okay, F12 means your element in first row and second column. So Fij indicates also displacement at I due to unit load at j. So you remember, displacement can be rotation as well as deflections. Unit load can be a reaction, or it can be a moment also. Okay, that means we are saying the flexibility method of analysis, it is a force method analysis, all those things are there. But when you come to the elements of the flexibility matrix, we'll be calling elements are known as flexibility coefficient. What are those elements? The elements of flexibility matrix are actually the displacement. Okay, so many times that can be a question in the objective type exam. The statement will be given. The elements of flexibility matrix are not forces, these are displacement. Okay, because in this case we have seen this is the flexibility coefficient. What is this element? This element is basically it is a displacement. F22, it is a displacement. Okay, all those elements of flexibility matrix which are known as flexibility coefficient. Flexibility coefficient, that means those are displacements only, not forces. And similarly, you will find that when you come to the stiffness matrix, the elements of stiffness matrix are going to be forces. That we will see later. So maybe we can write order of matrix is the number of coordinate chosen for the solution of the problem. Suppose if you have only two coordinate like our problem, your matrix will be, order will be 2 by 2 matrix. If you have three coordinate, your matrix will be 3 by 3 matrix. That is why when you are going for a very highly indeterminate structure, again your manual calculation will become very difficult, because if you have a 20 degree of freedom, 20 unknowns, extra unknowns, static indeterminacy is 20, maybe your matrix order will be 20 by 20. That will make it difficult when you come to the manual calculation. So that is why we have to put everything in the software so that it can be solved. Okay, so element of flexibility matrix are displacement, flexibility matrix will be always be square matrix. It will be always square symmetric matrix. Okay, and elements along diagonals will always be non-zero and positive. Okay, so that you can verify in all the problems. The elements along the diagonal f11, f22, f23, sorry, f33, like that. All these diagonal elements will be non-zero and it will be positive. So these are all can be asked in the exam statement MCQ type. Okay, the elements all the diagonal elements in your flexibility matrix will be non-zero and positive. And when you go to the other element, the cross diagonal element f23, f13, those elements can be maybe 0 or it can be negative. You have to see the direction also. It can be negative also. So matrix will be always the symmetric matrix about its diagonal, main diagonal, so that we can get from the Maxwell reciprocal theorem. Fij will be always will be equal to Fji. So you can say that your flexibility matrix will be always symmetric. Okay. Okay, flexibility matrix can be calculated only for stable structure in which there is no rigid body displacement. Okay, so whatever we are applying, all those applicable only for a stable structure. Okay, you can apply all those things only for stable structure. So by default, all those that condition will be satisfied by automatically. Okay. Okay, so we will see some more examples. Okay, so what you have in this slide, how to find flexibility matrix. So if we have this case, I think it is not a problem. Okay, we
Uh,
will.
sir, sir, will you take the second class means 12 to 1 also?
Yes,
Means the DC.
this will be afternoon,
Okay, means actually
2:15.
5 hour right now. That's why.
Maybe Viva will be at that time, 2:15.
Okay, 2:15 to 3:15.
I don't know how much time it will take. So afternoon hour will be taken by Padma Madam. I will not be taking.
Oh, okay, sir.
Okay. Okay. Suppose if we have a structure like that, we have a continuous beam. So we have four coordinates 1, 2, 3, 4. Okay, so in this case, our matrix is going to be 4 by 4 matrix. Okay, maybe we'll see this type of problems also. So, so in order to generate the jth column of the matrix, a unit force is applied at coordinate j, and displacement at all the coordinates are determined. These displacement will be construct the jth column of the flexibility matrix. And that is what we are doing in the previous example. Okay, and here we have four coordinates, so your flexibility matrix will be 4 by 4. It is going to be 4 by 4 matrix. Okay, 4 by 4 matrix. So there will be 16 elements in this. Okay, so we can get the first column of your matrix. You have to apply your unit displacement at corresponding to, you have to apply unit force. Take your simply supported beam and apply a unit force corresponding to your this coordinate. It is a clockwise, so we have to apply unit moment in the direction clockwise unit moment like this. Then find out what is the rotation at 1, that will be the first element, and next find out what is the deflection at point, what is the deflection here, that is the second element. Next find rotation at this point, that is my third element. Next find deflection at this point 4, that is the fourth element. Okay, so generally you can say that in order to generate the jth column of the matrix, a unit force is applied at the coordinate j. Okay, and displacement at all other coordinates are determined. That will form your jth column. So similarly, you can get all your columns. Okay, so that procedurally we have done in the previous example also. Similarly, other columns of flexibility matrix can be developed. Okay, 4 by 4 matrix can be developed. Okay, so with that we'll go to the next. We'll take question. We'll take 2 3 questions, and okay. Okay, we have a simply supported beam also. Then we have a continuous beam. Okay, and that's it. Okay. So how much is possible today? We'll complete that. After that, we'll go to the truss. So from beam, we will see 3 examples only because of we have very less time. So we'll explain 3 questions. You can go through that more question also. You can refer Bhavikati think it is given one chapter, flexible matrix method. You can refer that. So first question, develop flexibility matrix for the cantilever beam shown below with reference to the coordinate shown. Take A is a constant. Okay, so I think I can explain this, maybe it is simple. So this is a cantilever beam. The given coordinate, we have to develop a flexibility matrix with reference to the coordinate shown. Okay, that is why the coordinate is defined: one axial, second rotation, third translation, third is deflection. Okay, these are the three coordinates are defined. So if we did not define, then also you can solve the problem. We will get same answer. But only thing is, suppose if somebody is taking uh, first coordinate is a deflection and second one is axial, then their elements will be different. Like the location of the element in the matrix will be different. Okay, but final answer, if you are solving for a if you are solving, if you are analyzing a structure, your final answer will be same, but your flexibility matrix also will be same, but location of the elements will be different. First row you may be getting in the second row. Okay, that is why generally these coordinates will be defined in the problem, so that everybody will be getting into same matrix, elements, everything will be same. So anyway, this is the given coordinate. First one is corresponding to axial, and second one is corresponding to deflection, perpendicular to the axis displacement, and third one is corresponding to the rotation, clockwise rotation. So one thing is clear: your matrix is going to be 3 by 3 matrix. Your F matrix will be, your flexibility matrix will be 3 by 3 matrix. Okay, so we have 3 rows and 3 columns, and first row and first column will be same, second row and second column will be same, third row and third column will be same, because our matrix will be symmetric square matrix always. Okay, so now we will solve one by one. We can get the first column of your flexibility matrix. The elements of flexibility matrix will be like this: F11, F12, and F13, F21, F22, and F23, F31, F32, and F33. Okay, the first we will solve these elements. The first column of the flexibility matrix you can get. You go to our structure, you take your beam, cantilever beam, and apply a unit force corresponding to this coordinate. What is this coordinate? It is a corresponding to axial deformation. So we apply, you take your cantilever beam, apply a unit force, axial force, let us say 1 kilonewton or 1 newton, apply unit force. Okay, and then you find what is the displacement. What is F11? Displacement at 1 due to load at 1. That means corresponding axial deformation, that is your F11. So what is the equation for axial deformation? If you have a P is a force, your axial deformation will be PL by AE. Delta is equal to PL by AE. So where P equal to 1, so you will get P into L by AE, so 1 into L by AE. Okay, your first column is given by like this. First column, the elements of the first column we can get. You take your cantilever beam, okay, and apply unit force, and this axial deformation find out. Okay, that will be your F11. Due to unit force at 1, due to due to this axial force, what is your deflection? That is your this one F. This is F31. Displacement at 3 due to unit force at 1. And what is the rotation due to the axial force? That is your F21. Okay, and if you have a cantilever beam, or if you have a bar element, and I'm applying axial force P, and then what is the value of axial deformation? Delta equal to PL by AE. Okay, the length of your beam is L. Okay, and due to the axial force, what is the value of your deflection? Let us say this deflection component, let me, this one maybe I will take it small delta. Deflection delta, deflection will be, there won't be any deflection, there won't be any rotation also, because we are applying the load is along the axis. It is only having there will be some change in length, there will be only some axial deformation. That is why at this corresponding to this load there will not be any deflection and there will not be any rotation. That is why this F31 equal to 0 and F21 also will be equal to 0. So that is your first three element. F11 equal to L by AE, F21 equal to 0 and F31 is equal to 0. Okay, that is your first column. So any doubts we have in this case? First column, how to get the first column? Any doubts? You can ask me now. So similarly, we can get these three elements, second column. So how to get second column? You take your cantilever beam and apply a unit force corresponding to 2. That means you have to apply a clockwise moment. Unit clockwise moment you have to apply. So let us do that. Take your cantilever beam. Take your cantilever beam like this. So to derive the second column means these three F12, F22, F32. And so you have to see the given, this is a given coordinate, so second one is a rotation clockwise. So I am applying a clockwise unit moment equal to 1. Okay, I am applying a unit moment, and due to this unit moment, what is the axial deformation? What is the axial deformation? That will be your F12. Okay, axial deformation F12, because axial deformation due to this unit moment, we have to find, what we have to find, these three elements indicate we have to find what is the axial deformation, what is the deflection, and what is the rotation. These three we have to find. Axial deformation due to this unit moment at 2, that is your F12. Okay, this is F12. Okay, and then due to this moment, what is your deflection? What is the deflection? That is your F32. So this deflection will be your F32. I am just giving the direction in the same as your given coordinate upward. So I am also taking here upward. Okay, F32. And the next one is, what is the rotation? That is your F22. F22. Okay, so it is F32 is a deflection and F23 is a rotation. F22, sorry. Okay, this is the second rotation due to a unit moment. It is F22. So now we can use our standard result, and suppose if we have a cantilever B and if we have a clockwise moment M, what is the value of deflection and what is the value of slope? And axial deformation obviously is 0. Axial deformation is 0. We are not considering that. But if you apply clockwise moment at the free end, how it will reflect? It will have a deflection in the downward directions. Okay, you can just take a scale and apply a clockwise moment using your figures. Apply clockwise moment at the free end, you will find that your deflection will be in the downward direction. Your scale will go down. Okay, there will be some deflection that will be downward. What is the deflection? Delta equal to ml by ei, ml square by 2ei. If you apply clockwise moment at the free end, you will have some clockwise rotation. So direction is important. Direction is important. Okay, so delta is equal, theta is equal to ml by ei. So rotation theta will be equal to ml by ei. So now we can say that if you apply unit moment F12, that is axial deformation, that will be 0 anyway. There is no axial deformation due to the moment. Axial deformation already we are taking always 0. So F12 will be 0. This will be 0. So what is the value of your the rotation, clockwise rotation? We have ml by ei, so that will be 1 into L by ei, that is L by ei. The same direction as the given coordinate. Okay, the coordinate is given clockwise, so that is also will be same direction, so clockwise. So we can positive, that is positive. And when it comes to deflection, that is an important part. And the deflection, the given coordinate is upward, right? But due to this unit moment, clockwise moment, so my deflection in the structure, that is your m is equal to 1, so L square by 2a, that will be in the downward direction, which is opposite of the given coordinate direction. That is why your element, this F32 L square, 1 into L square by 2 EI, but that will be negative. Okay, that element, this will be a negative sign we have to keep, because the direction deflection is opposite of the given coordinate direction. Okay, that is why this one will be negative. That is the second column. So now we have to derive the third column of the flexibility matrix. The third column we can get, you go to take your cantilever B and apply a unit force corresponding to this coordinate. This coordinate is a you can say vertical, so you can apply a unit force of like this at the free end. Okay, so you take your cantilever B, apply unit force 1 kilonewton like this. Okay, and due to this, what is the axial displacement? That is your F13. Okay, because this deflection is, it is a coordinate is 3 and axial is 1, so this is a displacement at 1 due to unit force at 3, so that is F13, and this will be F23, and your deflection corresponding to the same this direction, that will be your F33. So now you can say that, like if you have a cantilever beam and if you apply if you apply force P in the upward directions, your beam will have, it will deflect like this. Okay, so if it deflect like this, it will have some vertical displacement delta, and it will have some rotation, anti-clockwise rotation theta. It will be anti-clockwise, this will be upward. So delta is equal to PL cube by 3 times EI, PL cube by 3 EI, and theta will be equal to PL square by 2 EI. Okay, so now we can say that what is the value F13? Axial deformation, anyway there is no axial deformation, so F13 equal to 0. And what is the value F23? F23 means displacement at 2 due to unit force at 3. Displacement at 2 due to unit force at 3. That means clockwise rotation due to this unit force at unit force. What is the clockwise rotation? So rotation you can find out theta PL square by 2EI, but this is not clockwise, it is anti-clockwise. Okay, because we are applying the force corresponding to the given coordinate direction upward. So this rotation theta is anti-clockwise. That is why again this term F23 will have a negative sign, because it is in the anti-clockwise direction, which is opposite of the given direction, clockwise. Okay, and the next we will go to F33, that is a deflection at this deflection at the free end due to unit force, due to upward unit force, that will be PL cube by 3 EI. So P will be always equal to 1, P is equal to 1, unit force we are applied, so this will be L cube by 3 EI. So this is what F33. We can see that F11, F22 and F11, F22 and F33. So F33 means unit displacement at 3 due to unit force at 3. F22 means displacement at 2 due to unit force at 2. Always if you apply clockwise moment, your displacement will be clockwise rotation, and if you apply anti-clockwise moment, you will have an anti-clockwise rotation at that point, and if you apply downward force, you will have a downward deflection, and if you apply upward force, you will have an upward deflection. Always your force will be in the displacement will be in the direction of forces. There will not be any question of negative sign when you come to F11, F22, F33. Okay, that is why in the statement I have given, always all the diagonal elements of your flexibility matrix F11, F22, F33, F44, etc. All these elements will be always non-zero positive. Okay, non-zero positive. But when you come to F23, F32, this when you come to this cross diagonal elements, we have to see the directions like this. If the direction is going to opposite of the given coordinate direction, we have to keep a negative sign. So this is my third column. Finally, it is my second column and it is my first column. So maybe we can write all those things. Third column is 0 minus L square by 2 EI and L cube by 3 EI. 0 minus L square by 2 EI. Sorry, what is this? L square by 2 EI and L cube by 3 times EI. Okay, so this is EI, not AE. Or okay, what is the first column? F11 is L by AE, and this is 0. It is 0. Okay, so L by AE 0 0. So this will be L by EI. Okay, not AE, it is EI. Just correct it. It is L square by 2 EI. It is also 2 times EI. Okay, 2 EI, 3 times EI. Sorry, 3 times EI. So this A is not there. This is my final flexibility matrix. Okay, I will edit this one and I will send you the slides. Because this I think it is what we got. Okay, same thing we got. So 0 second column will be 0 minus 0 plus L by EI and minus L square by 2 EI. 0 plus L by EI minus L square by 2 EI. Okay, this is how we have to develop the flexibility matrix for a given problem. Okay, so we have any doubt in this case? Have any doubt in this case?
Sir, can
Any
you again
question?
repeat the first column?
The first column, okay. The first column, you take your cantilever beam and apply unit force corresponding to the first coordinate. So what is that force? It should be axial force. And when you apply axial force to the bar, okay, this is the axially loaded member. We are just applying axial force. It will have axial deformation equal to PL by AE. Delta equal to PL by AE. So I am applying unit force. So this will be 1 into L by AE. This is the year 11 F11 displacement at 1 due to unit force at 1. So that is where L by AE. And the next element is F21, that is a rotation at the free end due to the axial force. So there will not be any rotation due to axial force. It will not have any rotation. There won't be any change of. There won't be any slope. It is just axial deformation. So that is why F21 is equal to 0. And when you and the next element is F31, that is a deflection at free end due to axial force at the free end. When you apply axial force, there is no deflection. It is only axially deforming. So this F31 also is equal to 0. That is why the
Yes,
first
sir.
column is L by A 0 0. Okay. So
Yes,
remind
sir.
things are yes. You have to just see it carefully. You can understand easily. Okay. So F2 we have completed this. Let us go to the next one. So this is the whole concept, only this much. Only thing is how to find the deflection due to this unit force. Only that part you may struggle a little bit if your basic structure analysis part is not clear. Only that part you will have some doubt. Okay, remind thing is very simple. Very simple. You have to remember you have a flexibility matrix, and that will be a square symmetric matrix. And elements of flexibility matrix is known as flexibility coefficient, and these are nothing but the displacement, not forces. And if you have a 3 coordinate in the problem, your matrix will be 3 by 3. If you have 4 coordinate, your matrix will be 4 by 4. And to get the first column, you have to apply unit force corresponding to the first coordinate and find out the displacement corresponding to all the coordinate. Okay, so you will get the first column. And to get the second column, you apply unit force corresponding to second coordinate and find out the displacement corresponding to all the coordinate. You will get 4 elements, that will be your second column. And like that you have to third and fourth column. Okay, only that is the procedure. And how to get the displacement, only that part we have to see how to get the displacement, only that is the question. Okay, only that is a discussion in the questions. So concept is very simple. You have to spend some, because this method may be new to you. You may not have done like this earlier previously. So that is why you have to understand carefully what is the flexibility coefficient, what is the definition, Fij, what is Fij? The displacement at I due to unit force at J. Okay, and again displacement can be rotation as well as deflection or axial deformation. Okay, and your forces can be axial force, or it can be a vertical force, or it can be a moment. Okay, and if you are getting in the displacement, it is not same as the given coordinate direction, then you have to keep the negative sign. Okay, I think only that much you have to remember, can solve anything. Okay, can solve any problem. Let us go to question number 2. So this question, the procedure is same, so there is no difference. Some formulas may change for the deflection, for the displacement calculations. So there is no other changes. So simply supported beam is given, and the coordinate is already given, like this 1, 2, 3, 4. 1, 2, 3, 4. So we will have a flexibility matrix. Your flexibility matrix will be like this. So we'll have F11, F12, F13, and F14, F21, F22, F23, F24, F31, F32, F33, F34. So F41, F42, F43, and F. So this is my flexibility matrix. That will be 4 by 4. That will be 4 by 4 matrix because I have 4 coordinates. So we can get we can get the first column 4 elements from where? To get the first column we have to you can get like the take your beam and apply a unit force, that is unit point load. Apply a unit force of 1 kilonewton like this, and get displacement at all the four coordinates. So once you apply force like this, we will have a bending will be like this. The beam will have a symmetric bending. Okay, and you can find what is the deflection at the center. Which is that element in this matrix? What is this element? Deflection at the center. What is that element in this matrix? Anyone?
Sir, what is the question?
F11.
Okay, so I was asking the what is the you apply first column, how to get take your beam and apply unit force at 1, and you can find the deflection at the center. Deflection at the center of your beam, that element will be F11. And what is the rotation at the center? What is that rotation? At the center we have some rotation. What is that element? What?
F12.
F12, or maybe you can say F21, because I'm just explaining in terms of columns. Okay, so that rotation at the center will be F21. Okay, because first apply unit force corresponding to first coordinate, you will get first column and first row. So we can say F12 and F21 both you can say, but I think this is I'm going with the columns. So that you can say that your F21 will be your rotation at the center, that will be F21. So can you tell me what is the value of rotation at the center in this case? What will be the value of rotation at the center? We have a continuous, we have a beam, simply supported beam, and I am applying a point.
0.
Yeah, deflection, rotation will be 0 because we'll have maximum deflection, so the rotation will be 0. So F21 will be 0 automatically. Okay, and in this case, you can find, next you can find what is the deflection at this point. Deflection at this point, what is that element? Deflection at that point, which element? I got these two elements.
F14. F41.
Deflection at this point. That means F3 displacement at 3 due to force at 1. That is F31. Okay. And the next we can find what is the rotation at this point. That is displacement at 4 due to force at 1. This rotation, this theta, that will be nothing but your F41. Okay, so these are the 4 elements. Out of these 4, 2 will be 0 automatically. 2 are 0, and to this rotation at the center F21, and displacement deflection at the point 3 coordinate 3, that is also will be 0 because we have a support here. Okay, so I can write your F11, that is equal to, if you have a load of W, your deflection at the center will be W LQ by 48 EI, and if you have a unit force, your deflection will be L cube by 48 EI. So we can substitute the value of L, that is equal to 12 meter. So 12 cube by 48 times EI. So you'll get the value of F11 and F21, that is, you can see the rotation at the center midspan due to unit force. What is rotation? This beam will have a unit symmetric bending, a deflection maxima here, and if you draw the tangent here, we'll have it will be horizontal. So theta will be 0 here. Theta will be 0. That is why your F21 will be equal to 0. And next we can find your displacement at 3. That means your displacement at this support due to unit force. If you apply force like that, we will not have any deflection at this point. Because there we have a support, so it cannot, we will not have any deflection, so it will be also equal to 0. Okay, and next we can find a displacement at 4 due to unit force at 1. Okay, and displacement means what is the clockwise rotation at this support due to this force. Okay, and if you apply load W at the center of your beam, so this is L by 2, it is also equal to L by 2. So the deflection at the maximum deflection will be WLQ by 48 at the center, and the theta rotation at the support. Okay, this theta will be equal to WLQ L square by 16 I think it should be WL square. Yes, so this should be L square. So what is the rotation at the support of simply support of beam subjected to constant load at the center, that is PL square by 16A or WL square by 16A. So I can use that equation W equal to 1. So 1 into 12 square by 16A. So we'll get some value 144 by 16 times EI. So these are my F11, F21, F31 and F41. Okay, that is what I have written here. The first element is, you can say same thing, 12 cube by 48 EI. So you will get some value 36 by EI. And F210, F310 and F41, that is equal to WL square by 16 EI. So 1 into 12 square by 16 EI. So you get 9 by EI, but you have to keep a negative sign. Negative sign is for anti-clockwise rotation. Okay, because this is clockwise rotation, but due to this loading, this rotation will be anti-clockwise direction from the horizontal. It is anti-clockwise. Okay, so that is why we have to keep a negative sign. So that is why this element will be minus 9 by EI. Okay, so now we got the first column. So I can get second column. You take your simply supported beam, apply a unit moment at the center. So your second column is like the second column. You take your simply supported beam and apply a clockwise moment of magnitude 1 at the center. Okay, so and then you can find what is what you have to find, what is the deflection at the center, what is the rotation at the center, what is the deflection at the support, what is the rotation at the support. These four results will be your second column. But to solve it, you should know the result. Which result? You should know this result. You can solve all those things very easily. Okay, but that is not part of this course, because these basic result you are supposed to know. Okay. Okay, this part will not be discussed now. It is a determinate structure. You can find out your rotation and slope at any point by using any method. You can use any method whichever you like. Okay, and if you apply clockwise moment exactly at the center, okay, it will have a deformation maybe like this. So this is the midspan. So let us say this is A, B, C. So your deflection at point center will be 0. It will not have any reflection at this point. It will have a deformation will be like this only. Here we will have hogging and here we will have sagging. So at the midpoint your deflection will be 0. And what is the theta at the midpoint? So that is the result I have given directly. Okay, I am not deriving this one now. Okay, so this is where you can derive it if you want. So theta B at the center will be 12 ml by 12 VI. And when you come to support C, we'll have deflection will be 0 because we have a support, and the rotation at the support C will be ml by 24 EI. Okay, these are the result. That means if you have a loading will be like this, then at the midspan, at this point we'll have some angle theta. We have clockwise rotation, and this theta will be 2 times of this theta. This theta will be something less. Okay, this will be just theta by 2. That is what you can see. This is ml by 12 EI, and this rotation will be ml by 24 EI. So maybe you can remember this result something like that. Because we are applying the moment at the center, so there we'll have maximum theta, that is ml by 12 EI, and at these two support we'll have a rotation that will be just theta by 2, provided you are applying your moment at the center. This will be theta, this will be theta by 2. And equation for theta you have to remember ml by 12 VI and ml by 24. Okay, now we can directly easily write your equation for your elements F12, F22, F32 and F42. You can easily write. Okay, this is my given case. We have a simply supported B, and this is the first component, first coordinate, second, this is third, and it is fourth. Okay, so you can find this is apply this unit moment and find out the displacement at 1. Okay, displacement at 1 due to a unit moment at the midspan, that is your F12. So F12 will be 0, displacement deflection is 0, so F12 equal to 0, and F22, that is your this second coordinate is a clockwise rotation, so the rotation at the midspan due to the unit moment at the midspan. So that is given by this one, ml by 12 EI. So m is equal to 1, so that is 1 into L is equal to 12, so by 12 EI. So we will get 1 by EI. Okay, and the next is F31, F32, that is a deflection at the support due to the unit moment at the midspan. So that is obviously it is 0. For the support there will not be any deflections. That is for F32. And the next element is F42. That is, this is the coordinate, that means rotation at the support due to the unit moment at the midspan, F42. So that is your ml by 24 EI. So you will get 1 by 2 EI. So 0.5 divided by EI. Okay. So the given coordinate, the direction clockwise, but due to this loading at this support, we will have a anti-clockwise rotation. Okay. The given coordinate direction is clockwise. Okay. This coordinate direction is clockwise, but the rotation coming at that point is anti-clockwise. Because we are applying clockwise moment at the center, so this section will have sagging. So this will be anti-clockwise moment. This is anti-clockwise rotation. So that is why this magnitude 0.5 by EI, it is negative. The negative sign is for anti-clockwise rotation, anti-clockwise direction. Okay. So these are the four elements, 0 and 1 by EI, and again 0, and then minus 0.5 by EI. That is my second column. Okay, that is my second column. Similarly, you can get third and fourth. To get the third column, you take your simply supported beam, apply a unit force at the support. That is very simple. Third column, you take your simply supported beam, okay, and apply a unit force at the third coordinate 1. So if you apply unit force at the third coordinate, what is the value of your, this point is B and this point is C. What is the value of your deflection at the center, rotation at the center, deflection at the support, everything is 0. Because if you are applying load directly to support, it will just transfer load directly to support only. Okay, it will not cause any bending in the structure, so all the element will be just 0, because the load is directly applied over the support. It will not have any bending, so your beam will remain straight. So that is why all this element will be 0. Okay, you can easily get third column. Okay, and the next you can get the fourth column, and fourth coordinate is this one, clockwise. So we have to take your simply supported beam, and apply a clockwise moment, unit moment at the support, at the right support. So if you apply a unit moment, it will bend like this. It will bend like this. Okay, so so now we can find if we have a Then what is the deflection at the midspan? That will be your that will be f14. Okay, and what is the value of theta here? Theta, that is your f24. And what is the value of your deflection here? That is your f34. And what is the rotation? This rotation, that is your f44. Okay, so for this case also we have a simply supported beam, and we are applying a concentrated moment at the right support. Applying concentrated moment at the right support. Okay, so for that case also, so I will give this result. You must be knowing at the support will have you can easily solve it by using conjugate beam method. Okay, you can solve it by using conjugate beam method. So we can get theta 1 if you apply clockwise moment like this. So if you have a beam, if you apply clockwise moment, your beam will have deflection shape will be something like this. Okay, so here we'll have a maximum theta, here we'll have some less theta, and this theta is equal to ml by 3e. Okay, you can easily solve by using conjugate beam method. And also I need one more result. What is the theta at the center? Okay, in this case we will not have a symmetric, you can say we will not have a symmetric bending, because we are applying the moment only the right support. So this side may go like this, so we'll have bending maybe something like this. Okay, it is not symmetric, it is not symmetric like this, it is symmetric. Okay, if it is symmetric, then your theta will be 0 at the midspan, but here it won't be symmetric, and you have to find what is the theta angle with horizontal at the midspan. That will be your f24. Okay, and that value theta I have already I'm directly giving you that equation. It is, let us say it is a midspan, and draw your tangent there and draw your horizontal line there, and we can measure that we can take this angle. Okay, that is your, in this drawing, that is a theta. Okay, the theta at the midspan, again you have to use a conjugate beam method if you want to solve it, or you can use any other method, because it is it is a simple determinate beam, and you can find what is the rotation at the midspan for this loading, and that you can calculate this, and you will get that is ml by 24 ei. Okay, so that means for f24 will be equal to ml by 24 ei. So m is equal to 1 and L is equal to 12 meters. So 12 by 24 ei. So F24 will be, so you can say F24 will be 12 by 24, so 1 by 2 ei. 1 by 2 ei. Okay, that is the value of your F24, and F14 is your again the deflection at the midspan. Okay, deflection at the midspan. So that is your F14. So deflection at the, maybe here F14. So that is given by ml square by 16a. So this result you have to solve it. This one I don't want to repeat. Okay. So because what you have to find out, that only that should be clear. Okay. This one F14 is given by your upward deflection. Okay, the deflection at the midspan. For this loading you can find unit moment. That will be if you have a moment of m, you will have upward deflection will be ml square by 16a, and our case where m is equal to 1, so this will be just 12 square by 16a. Okay, and again this deflection is in the upward directions, deflection is in the upward directions, so that means you have to, your elements that there will be negative sign, ml square by 16a, so that will be minus 9 by ei. Okay, and f24 is minus 1 by 2 ei, f34 is 0. Okay, and that is support, and f44 is your ml by 3a, so 12 by 3, 4 by ei. These are the elements we are going to get. Okay, okay, and one more thing, this one also will be negative like this. So if you the element, this one f24, this rotation at the midspan, So it will be, the deformed shape may be like this. Deformed shape will be like this. This is the tangent. Draw the tangent at the midspan. This is my tangent. This is my horizontal. What is the direction of your theta? You have to start from your horizontal to the tangent. So this will be anti-clockwise. Okay, but the given coordinate is clockwise. Okay, so that is why this will be negative. That element also will be negative. Okay, so you have to revise it and you have to solve it. That all you will understand. Or early, I think at least you should understand the sign convention and all is element. What is element? How to find out that? That should be clear. Okay, so apply unit format. Find out deflection at the center, rotation at the center, and deflection at the support and rotation at the support. That is what your four elements: F14, F24, F34, and F44. So now I got all the elements. So I am writing the flexibility matrix, and you have to solve it. For the problem, you have to solve it your own. Then only uh, you will be clear. Otherwise, you will have a lot of confusions. So final matrix will be like this, where F matrix will be 1 by EI. So 1 by EI. This is equal to 36. I'm just giving you the final matrix. All the elements we got the answer. I'm just putting in the matrix. 0 0. This is 0. Okay, and this will be 0 1 and 0 minus 1 by 2, and this will be 0 0 0. And oh, let me check that. F F33 what was the value? Okay, it is a special case. Okay, here maybe that statement can be, you can see this here. In this case, our diagonal elements also coming as 0, but it cannot be negative. Okay, only that is the conclusion. The diagonal elements cannot be negative. So in this case, it is going to 0, because it is a special case. It is not the loading condition actually, because we are applying the load to the support directly. So obviously in that case there will not be any deflection in the B. There will not be any displacement in the structure. All the elements are 0. That is why this element also coming as 0. So minus 9 minus 1 by 2. You solve this question. This question is a good one for practice. So if you are able to solve it correctly, you are on. Then it is everything is clear. You can say. Then all the concept will be clear. If you try to solve it your own and compare your solution, if you are getting the same, then it will be very, I think your concept will be clear after that. Okay, so you can see this matrix is a flexibility matrix, and it is a 4 by 4 matrix. It is a matrix, square matrix. You can see that. Okay, this is the flexibility matrix. You have to see this again. Okay, you go through the solutions step by step and try to solve it. Okay, if you have any doubt, we will clarify in the next class. Okay, that is the second question. It is also, we are just deriving the flexibility matrix. So after that we'll go for one question analysis. A continuous beam will be given, and I will give solution. You can go through that. So maybe today I cannot complete, but we will start it. Okay, so you can do that. Okay, you were on. It is not difficult. Only I have to, after flexibility, up to flexibility matrix, you can do that. Okay, so after that we will discuss in the next class. Okay, so we can see a two-span continuous beam is given and analyzed by using flexibility matrix method. Okay, so it is a 10-mark question, I can say, if it is a subjective exam. The first we can find the static indeterminacy, that is a 2. 4 minus 2 2. So remove 2 support RB and RC to convert into a statically determinate structure. Okay, so you take this is a coordinate 1, it is a coordinate 2, RC and RB. So now we got your determinate structure. Okay, and we can find first this one. We can find first you can develop the flexibility matrix. First we will apply unit force at, you take your basic determinate cantilever beam and apply a unit force at the free end in the upward directions. Okay, so finally you will have a flexibility matrix that will be 2 by 2. Okay, F11, F12, F21, F22. This is my flexibility matrix. Because my The degree of static indeterminacy is 2, so that is why this is 2 by 2 matrix. Okay, so here we are defining the coordinate, direction, and numbering we are doing. So we have to do the analysis only. Okay, so first step is you have to develop the flexibility metric, and that part is same as the previous two examples. Okay, and first we apply a first column of this matrix. You can get to take your cantilever beam and apply a unit force here. How to develop the first column? How to develop the first column, and take your cantilever beam without any load and apply a unit force upward direction here, and then we can find out. This is homework. Okay, I will not be doing. You can find out what is the deflection at the free end. Simple, LQ by 1 into LQ by 3EI. And what is the deflection at this point? Coordinate 2. This will be your F1, displacement at 1. Sorry, displacement at 2. So as per my number, this is 2. Okay, so I'm explaining the second column then. I applied here, so this is second column, not the first column. Okay, this element is displacement at 2, deflection at 2 due to unit load at 2. That is at LQ by 3 times EI. And this element will be displacement at 1, that is a deflection at 1 due to unit load at 1. Sorry, unit load at 2. So F12. So F12 you can find out. We have a cantilever beam and apply some load P, and you can find the deflection at any point. Simple problem. You can find the deflection at this point. That is your F12. Okay, you can use any method. You can use shortcut method. You can use a load shifting method, which already discussed in our strength of material. You can shift this load, and here equal and opposite force, and you will have a moment and a force, and then you can find the deflection at that point. Okay, that is your second column will be like this: F22 and F12. F22, F12 you can get. So this is F22 is equal to your LQ by 3 times EI, and this one you can solve it. Strength of material problem, you can get that easily. You can get that. So maybe you have to do like this only. Suppose I have a cantilever beam and I have force here P, and let us say this point is midpoint or not. It is not midpoint. Some point A and B. So my objective is at the free end you can easily find out the deflection, that is PLQ by 3 times EI. That is simple. So I have to find the deflection at any other point. Maybe this point I want to find the deflection. This is A and this is B. Total A plus B equal to L. So what I have to do is you take your cantilever beam and shift this load to the center or this point. Shift that load. Okay, I have already, I think we have a video also for that problem. We have already discussed this one. You take this load and apply here, maybe not take the, you have the load here and apply an equal and opposite force here. So now what will happen? You can take this one and this one, equal and opposite force will create a clockwise. It will create a couple clockwise moment of how much? This is the magnitude is P into B. This distance is B, so this moment is PP. And then in addition to this couple, I have the downward force P. I have the downward force P here. And now what is our objective? We have to find the deflection at this point. This deflection I can find, this is equal to delta 1 plus delta 2. Delta 1 is a deflection at this point due to this point load, and plus delta 2 is a deflection at this point due to this moment PB. So we'll have two terms. That is what here I have written. Okay, that is what here I have written. You can go through it. You can go through that. You will get your answer is 45.33 by 8. Okay, and that is the second column. And if you want to develop the first column of your stiffness matrix, flexibility matrix, you take your beam and apply unit force here. Apply unit force here like this. Okay, and then you find the deflection at this point, that is F21, and the deflection at this point, that is F11. Okay, and if you have a point load here and your deflection at this point, I think it is you can use this equation. P into this distance, you can take it as L. Okay, so you can get 21.33 by EI. And F21 we can directly find out by using like this. So we have a beam and we have load here, so it will deflect up to this point. It will have a bending, and after that we don't have any load, we don't have any bending moment this part, so it will be remain straight. Okay, and now I can easily find out I can easily find out this deflection delta 2, that will be this deflection. I can find delta 1 21.33, and this reflection will be delta 2 will be equal to delta 1 plus you can find out this angle, and if I know this angle from this triangle I can find out this length. So let me call this length is y. So delta 2 will be equal to delta 1, this is delta 1 plus y. That is what I have written here. So this is nothing but this distance is how much will be this length, that is a slope at this point, that is a PL square by 2EI. Slope at this point multiply with this distance 3 meter. So PL square by 2EI into 3 meter. These are all basics, and you have done in structural material. You can refer that. If you are not getting this value, please refer your structural material. So now I got all the metrics, all the stiffness, all the flexibility coefficients, elemental flexibility matrix. Then I can put in the form matrix. That is my flexibility matrix. Okay, that is the flexibility matrix. Okay, so remind things anyway. It is not possible to complete today. So we will see tomorrow, next class, tomorrow. Okay, tomorrow we will continue up to the flexibility matrix. It should be clear. And from here we will continue tomorrow. I will give you the complete solution. You try to solve it complete. Okay, try to solve it and try to understand it. So anyway, we will discuss tomorrow from here. Okay, I am stopping with this for today, and we'll continue tomorrow, and hopefully we'll complete it by tomorrow.